Let's derive the conservation of momentum for a finite control volume. Remember, finite control volume is going to give us the integral form of the equation. So let's start once again with the concept and then turn that into math. Conservation of momentum says momentum is neither created nor destroyed, which lets us write a balance equation of the form that the rate of change of momentum of the system is equal to the net flow rate of momentum into the system. Net flow rate there means momentum in minus momentum out, plus the sum of external forces acting on the system. So again, this is the rate of change of the conserved quantity is equal to the interactions that change it. So part of this you're familiar with before, right? Rate of change of momentum of the system. Well, momentum, remember, is mv, so rate of change of that is d by dt. And so for a constant mass system, the m pulls out of the derivative, and you're left with m dv dt on the left here. And so that just becomes ma. And if it's closed, there's none of this business of flow rate going in and out. And so it's just the sum of the external forces acting on the system. And so this is F equals ma. The challenge that we're going to run into is that we can have flow that causes extra momentum to go in and out of it. You could picture this, for example, if you were on ice skates sliding along. That's the MA part on the left. Sum of forces, maybe somebody's pushing on you, or maybe there is a friction force on the skates that's slowing you down slowly. But as you're moving, imagine somebody tosses you a basketball, and then you toss that basketball away. That's the flow rate of momentum in and out. That basketball carries momentum with it, and so when you catch it, your momentum will increase, and when you toss it away, your momentum will decrease again. So that's what we're going to look at here. Let's start with the first term, the rate of change of momentum. Remember that momentum looks like mv, so if we want it for a differential element, we would write this delta m dv. And just like we've done a few times, the differential mass is really just the density times the differential volume. And so this is differential mass times the velocity vector v. We can, of course, then integrate this to get the overall momentum, and it's going to look like the integral of this differential momentum just gives us momentum. And the integral of rho v dv here is going to give us the momentum. And so we've got this triple integral over the volume of rho v dv, where this is velocity and this is volume. And so if we want the rate of change of that to go into the first term of our balance equation here, we just need to take the time rate of change of this term, which is d by dt. So d by dt of the momentum of our system. What you'll notice is this looks a lot like the rate of change of mass in the system. The only difference is this velocity showed up. Next, we need the flow rate of momentum into the system. That's this term here. The third term's easy. It's just the sum of the forces acting on it. So there they are. And so the second term will finish this out here. We just need to find the flow rate of momentum into the system, which we can get like so. Remember that momentum is mv, so the flow of momentum must just be m dot v. A differential amount of that looks like a del mom dot m dot, or del m dot times velocity vector here. And so once again, just like in mass conservation, this mass flow rate differential looks like rho v dot n dA. So that came, you saw that in mass conservation. So it's the same thing, just multiplied by v. We integrate that to get the total flow rate into the system. So we integrate the left side, we get momentum flow. And on the right-hand side, we integrate this over the area. And so we get the integral over the area of rho v dot n times v dA. Now, v dot n is positive when we have flow out of the system because our normal vectors point out. And so if we want the net flow rate into the system, we actually need to put a minus sign on there, right? The opposite of out is in. So the flow rate in looks like rho v dot n times velocity dA. And once again, you'll notice that term looks just like the mass conservation, except that we've got an extra velocity in here. So we combine that, sub it all into the words that we wrote out to get ourselves a balance equation. And what we discover is that we have the rate of change of momentum of our system, rho v d volume, is equal to minus v rho v dot nda plus the sum of the forces. In other words, this first term is still just the rate of change of momentum of our system. It's ma, right? Rho of dv, that's m. D by dt of the velocity, that's a. So this is an ma term, basically. And this term is accounting for the flow rate in and out. This is the proverbial basketball that I was telling you about earlier. Don't worry, we'll do lots of examples where we show how to actually apply this. Right now I just want you to look again and say, okay, well, this first term's ma, second term is flow of momentum in and out. And of course, just like everywhere else, that has to be equal to the sum of the forces acting on our system.